even think of testing this again, and so,
Oh, it's a virtual exam.
well, what if?
Oh, I see.
Since because he's supposed to be out of town, but since he's here now.
Oh, I forgot to mention. I'll send an announcement, but I'm not going to be here next Tuesday. Actually, too. I'm planning on being sick that day.
Oh, okay.
I'm planning on being sick with the condition of gas is too expensive. Or is it more like they don't pay me enough to be here every day? So, but yeah, we're gonna have virtual lecture on Tuesday. I'll send it.
Every year.
It's terrible.
Oh, because I've done these in high school. Because we're gonna Long Beach Grand Prix every year. And I have a vision problem. It's like, oh, what's it? I just can't see myself coming to school.
There you go.
I never told them that during when I was there. Went back afterwards to pick up my diploma because I didn't want to wait that graduation night. I was talking with the dean back then. She's like, "You really missed like 4 days of school." I went, yeah.
At the same time every year.
She's like, roughly about the same time. I went, yeah. She's like, you could have been sick at that same exact time every year when I had a vision problem. Like, what? Just couldn't see myself being here that one random Friday. Next year, I may be missing one.
Oh. Okay. Work. Can't pull that one on work.
I'm at a new job.
That's true.
Depending on what I end up taking into. But I'm kind of hoping for that city job back. And if I'm scheduled to work either day or night, feel a little bit too. Unless they hire me and then put me in with Mary, and it'll be easier because we do work 4 10s. Go to the career fair today? Yeah. Go to the one next week too? Oh, yeah, I will go. Because next week's is just the STEM. Yeah, today we just, a general. I didn't bother. How many companies for you? Next week's is going to be the big one. Anyways, I'll go there. Anytime for the weekend? More planning.
More planning.
When
They were done.
December.
Because.
Basically, right. Right after the last week of classes.
just like we got 8 weeks left after protection.
It's crunch time.
I'm counting down the weeks.
Me too, but for different reasons.
Well, that was
You try it.
yesterday. On Wednesday, so 20 hours. Did you pull the trash cans? Yeah.
So you might have.
8 more weeks in a day. Well, no.
No.
He's like, at least you're on.
They're not saying yes.
Yeah.
But I don't know whether it's because project
Or I'll text it done. Great. And then 6 weeks. It'll get a lot better, but you have. Sure. Because I was on top of it, seen that whole lot in the summer.
So that's better than what I had. Seems
My internship, I don't think my parents know, I just, because they see that.
no, oh, it says,
I'm not working.
Hey,
Yeah.
I remember this is advice.
Right.
Either way. You should.
I still find it. Trying to have time to do.
I know there's a.
Others. Not stuff.
When you're at school, that's all you can really do. So just
Yeah.
mental, physical time too.
I'm trying to find at least one day a week. I guess this comes. That's gonna be Sunday. Series.
Oh, nice.
Just a small coverage. So.
Yeah.
And we'll just go crazy.
Gotta take care of ourselves. And harder and harder to do nowadays, though. So many demands from their employer, just lots of stuff.
You just try to get everything done. I was bringing the candle off all things, did it to the 12. And
There's only so much, there's only so much sleep that you can.
yeah,
Only
and
so
then
much.
at a certain point, I'm like, I can't. Something had to give and it wasn't good in school.
I'm glad people are like realizing that more and more nowadays. But I remember when I was a student, like it was all about that grind. People would like brag about, oh, I only slept 2 hours last night studying. Why do we do that?
I'm a morning person, I could get up at 3:30, 4 o'clock.
And they closed it already. But there was
No flying.
position.
Okay, but now, so then that's.
I applied already.
Oh, wow.
Give it a shot.
15 hours, yeah.
They were telling me like
It's.
the senior
I
grade.
ate lunch at 11.
Yeah,
So.
majority of the staff is like.
They're early lunchtime.
Yeah.
Really.
They eat breakfast at 5. Or shortly after, so.
Yeah.
I got used to eating lunch at 11 and stuff. So.
What I'm gonna do is like.
You must be hungry now. I'm almost starving.
All right. Yeah, home at 7 o'clock at night. I still want to.
While I was thinking.
It was. I didn't see it. If mom didn't make anything, why did it like that?
I haven't looked here in a while.
Do that.
All I've been doing-
That was great.
Why? I live off of that.
all I've been doing is advertising.
They have a snake.
It's really good.
I was like, oh yeah, here's this for you.
Oh, yeah.
Yeah, that's why like.
It's the best.
If they're waiting for.
I miss that.
I
Prepare all my own food. When I cook now, I cook a lot so that I can have leftovers.
Oh, that is.
Okay.
Yeah, I'm trying to limit how much I go out.
Yeah.
Throughout the week.
It's expensive.
Well, even before it got really expensive, I tried to limit how much I did.
Yeah.
So simple fact that. Yeah, you'll get fat. Especially if you go to- Yeah, oh yeah, you could just too.
But I know you.
Food's really expensive now too. I spent like $15 on a meal at McDonald's last time. It's like, oh,
Don't go down, don't go there.
You're on.
Go to, Abbott.
It's on
Friday.
LinkedIn.
it's expensive too. Yeah. And this pisses me off with the Abbott here is that the prices on their menu are not consistent with the price of the charge. It's like, oh, I'll get a burger and then it's like 70 cents more expensive than what they have on the menu. But like I didn't want to put on my Karen hat to help about it. Just avoid it.
Finite work, you have substance clear. Place. Well, what you're getting is, yeah. I could be one of them. And it's actually helps. So, well, the worst part of that is the rice. I like rice. I'm ready for it.
Gotta have some vice.
I think like 20 minutes. Yeah, I have to make.
Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Hanging in there? Busy? Yeah. There's a career fair today. I know there's a career fair next Thursday as well, so I know probably a lot of you will be going to that. So, definitely make use of it. So those career fairs don't come around, that often. So I know that I know the one next week, I think is actually very relevant for engineers, the STEM one, yeah. And so, if you haven't registered for it, if you're not considering going to it, I would consider it. I would definitely try to go to it. And remember that this class is always recorded. And so we don't have an ANSYS activity next week. So next week is just going to be a pure lecture. And so you can catch up on the lecture just by watching the YouTube video afterwards. Was there a question over there?
Yeah. What about where is the STEM fair happening?
I think it's in the Titan Pavilion, right? I think it's in the TSU.
And when is it next week? Exactly.
Next Thursday. So I think the time is going to be between 3 and 5:30, something like that. Something like that. I haven't checked the exact details in a while, but definitely I would definitely check it out. Because I know a lot of you guys are graduating and post-graduating, and so definitely check out those career fairs when they come on. It's not that often, and it's not that often you see a bunch of employers kind of together and be kind of one place where you can kind of talk to a lot of these. So, yeah, 3 to 5:30. 3 to 5:30. There you go. Yeah. And so even if you don't, and because I know kind of the experience nowadays is that a lot of these recruiters will just tell you to apply online anyway. It's still good to kind of go and talk to them and kind of see what they're looking for, and then tailor your kind of resume and your application. So definitely check it out. And there's a reason why these companies came to Calcic Forward to advertise. It's because they like to hire our students. So that's always a good thing. All right. And so with that said, let's go, for today's lecture, the plan is just to continue on with the direct stiffness method, okay? And so last class, on Tuesday, we introduced this concept of the direct stiffness method. We introduced the idea of element stiffness matrices and assembly, okay? And so there's only a couple more steps to the direct stiffness method. We're gonna apply boundary conditions, and then the solve. And actually the solve is actually the simplest part, okay? So we'll finish that up today. We'll do a couple of examples, and then if we have time, we'll go ahead and move on to truss elements, which is kind of the next thing. Okay. All right. I think that's it for my announcement. So remember to keep working on activity 4. It is a long one, and so if you haven't made much progress on it, I would definitely do that. And then kind of in the background, make sure you're working on the midterm project as well. So. I've already gotten a few questions on the midterm project, which is really good. And so make sure you get started on that early so that you have your chance to ask your questions. Okay. All right. Any questions? Any questions or anything I can answer before we get started for today? Yes.
So, midterm, would it be a solving problems, or are we going to work on the answers too?
Yeah, so the midterm exam is planned for basically the last lecture before the fall recess, so right before Thanksgiving. It's going to be based on this stuff, and so it's going to be all hand calculations, so no ANSYS. So kind of what we're doing right now, I consider kind of separate from ANSYS. And so the way I basically assess you guys on the ANSYS is the ANSYS activities, the midterm project and the final project. And then for this stuff, the theoretical stuff, there's going to be one homework assignment. Basically after the midterm projects due, and then the midterm exam. So those things are kind of separate.
Are you punishing us with hand calculations?
We have to do this. This is not just an ANSYS class. This is a finite element class overall. So we have to go with the theoreticals. All right. Any other questions on this stuff? Okay. All right, so let's go ahead and continue. So what we were doing was the direct stiffness method. And in particular, we were on the boundary conditions. Okay. All right, so let me kind of refresh our memory, kind of what we did last time. Okay. And so far, we have covered 2 steps of the direct stiffness method. The first step being this whole idea of the element stiffness matrices. And so if you recall that from last time, whenever you have any kind of finite element mesh, right, your finite element mesh is comprised of a lot of elements, right? And so the idea with the element stiffness matrix is that for each element, you're going to create kind of this matrix system. And so it's a system of linear equations that describe the physics of that element. Okay. And basically, you're going to do this for every single element in your mesh, or every single element in your discretization. Okay. All right. And so step 2, once you have the element stiffness matrices for every single element, is to assemble them all into one global system. Because what we want to do ultimately is we want to solve for the solution, which in our case is going to be deformation. So deformations at all the nodes in our mesh. Okay. And we can't do that unless we have everything kind of assembled into one big linear system. And so by the end of these 2 steps, we have kind of a very large, what I call a global linear system. And so the size of the global linear system, of course, is going to depend on how many elements, how many nodes that you have in your mesh. But in particular, let me go ahead and write out the one that we were working with on, but we were kind of in the middle of an issue. And so an example, we have a 3-node system with 2 elements, okay? And so that means our global linear system is going to be 3 by 3. And then our global linear system looks like this: Ka minus Ka, 0 minus Ka. Right in the middle of that global linear system, we have the overlap. And so we have the overlap between element A and element B. So this is Ka plus Kb. Minus Kb, 0 minus Kb, and positive Kb. Okay. But remember, the way that we got this was that, we inserted the element stiffness matrix for element A kind of in that top left corner, because we know that element A was connected to nodes 1 and 2. And then for the element B, we know that element B was connected to nodes 2 and 3. Okay. And so when we inserted that element stiffness matrix into the global system, it would go in that bottom right corner, because those correspond with our, nodes 2 and 3. Okay. So this is great. So this is a good place to be, because now we basically have this kind of global kind of linear system. Okay. And so ultimately, what we're going to do is, this global linear system here represents kind of a big system of equations, right? And so in this particular case, we have 3 equations and 3 unknowns, right? So ultimately, we want to solve this for our unknown deformations. Because the deformations D1, D2, and D3, those are all of the unknowns, right? And in theory, in theory, you know, we have everything that we need to do that, right? 3 equations and 3 unknowns, right? And so in theory, you know, this should be possible. Should, of course, being the operative keyword, okay? And the reason I'm kind of saying that with a lot of shade or a lot of doubt is, of course, this is not going to be possible the way that it is, okay? And so even though we have 3 equations and 3 unknowns here, there is actually some redundancy in these equations, okay? And so if you took this linear system, in fact, if you took that matrix and you tried to find the determinant of that matrix, what you're going to see is that its determinant is 0, okay? And so what that means is that we have a unsolvable system. And that's kind of very easy to see kind of even without that too, because if you look at this matrix, what we have is a symmetric matrix. So if we kind of, you know, slice it that way, we can see that, you know, our matrix is the same above and below that. Okay. And so what this tells us is that in order to solve this system, we have to make some modifications to this system, you know, in order for it to get a solution. Right, so that's you know kind of the motivation for boundary conditions from a mathematical point of view. Right? If you think about this from the physics side, you know it makes a lot of sense too, because we haven't applied any boundary conditions to this at all, right? And so for all we know, for all what the system represents, is just we just have 2 springs that are just kind of sitting next to each other, you know, on a table or something like that. Okay? And so there's no constraints, there's no loads, there's no forcing that's causing these springs to change. And so boundary conditions are going to give us basically the way to mathematically modify this into something that we can solve. And so when we're applying boundary conditions in this case, you know, I want you to think about them in terms of, you know, the boundary conditions are going to modify this linear system. Okay? And so if you recall from our discussion of boundary conditions, you know, in ANSYS, we know that we have primarily 2 types of boundary conditions. We have constraint type boundary conditions and we have load type boundary conditions. Okay? So we're going to use that same distinction here, and each of them is going to have a unique kind of mathematical effect on this system. So let me go over let's go over the constraint type boundary conditions first, and then we'll go over the load. And so remember, the other name for the constraint type boundary conditions are the Dirichlet boundary conditions. So you may hear me say that just subconsciously, just because that's how it is in my mind. But I'm gonna try to use this terminology of constraint type, just because it's I think a little bit more physically easier to see. Okay. And so if you recall from the constraint type boundary conditions, what they basically did was they forced the solution to have a certain value at the boundary condition. And so our most common example for the constraint type boundary condition is our fixed support. So we've applied this in every single ANSYS activity so far. And so the fixed support basically forces the deformation to be zero at the locations where we apply that boundary condition. So let's kind of remind ourselves what our original geometry looked like, or what our original kind of figure looked like for this problem, and let's see where we can apply our constraint type boundary condition. Okay, so in this example, we had two springs connected end to end. Node 1 was connected to the wall. Node 2 was the one that connects the two springs. And our two springs were labeled element A and element B. So we have KA and KB. Okay. Okay. And so if we look at this configuration here, let's look in particular to node 1. Okay. So node 1 here is attached to that wall. And so if node 1 is attached to the wall, for all we know, that wall is fairly rigid, so that's not going to move. And so what we can basically say is that we can apply a fixed support boundary condition, or that's kind of what the figure defines at node 1. Okay. And so what do we know about fixed support boundary conditions, right? So fixed support boundary conditions, we know that the deformation there is going to be 0. Okay. And so we already have a label for the deformation in node 1, right? So the deformation in node 1, we gave the symbol D1. Okay. And so if we're going to apply a fixed support boundary condition at node 1, that means that D1 is going to be set equal to 0. And that's something that we're going to just enforce. We're going to force it to happen. Okay. So that makes sense, right? So we have a node that's fixed to a wall, and so if it's fixed to a wall, that means its deformation is going to be 0. Any questions on this so far? Okay. All right, so that's great. Okay. Next thing I'm going to do is I'm going to do something kind of strange. So I'm going to rewrite this equation, right? So we have a very simple equation here, D1 is equal to 0, but let me rewrite it in a very, very strange way. So let me say that this is the same as D1 plus 0 times D2 plus 0 times D3 equal to 0. Okay. In fact, another way to kind of take this a step further, we can put a coefficient of 1 in front of D1. Okay. So these two equations here are exactly the same. So why did I do this? And so, well, you could say that, I like writing math stuff, so which is true. But when it's written in this form, we can actually write it in vector form, matrix. Because what if we do this? And so, what if I take all these coefficients, and so we know we have coefficients of 1, 0, 0. Okay. Let me put that into a row vector. And then let's multiply this by a column vector of D1, D2, D3. And all this is equal to 0. And so you know that if you take a row vector, you multiply by a column vector, it's basically like taking the dot product between those two. Okay. And so if you take the dot product between those two shown vectors, you're gonna get the same thing as above, which is the exact same thing as the box equation at the top. Okay. So why would I do this, right? So why would I go through this trouble of putting that equation, which was already kind of too long, into a matrix equation, which is even bigger, right? Because now that we have it in this form, we can actually incorporate this into our global linear system. Let me go ahead and draw out or write out our global linear system one more time. So for this problem with 3 nodes, it looks something like this. And all this is multiplied by D1, D2. Okay. So that's what we have so far. But what I want to do is I want to incorporate kind of this boundary condition equation into this matrix. Okay. So let me do this. So let's, we know that this boundary condition is acting on D1. Right? In fact, we have a 1 in that kind of D1 slot. And so let me take this first row of this matrix here. So let me replace this with the equation that I have above, because you can see we have some similarities. And so just like the matrix equation above, we're multiplying it by this column vector of D1, D2, D3, right? So that's the same. And then as part of the matrix, we have a 3 entry wide matrix. And so this is actually kind of the perfect length for that as well. Okay. And then instead of F1, right? This F1 kind of represents the right-hand side of that equation. Well, technically right now it's on the left side. And so if we replace this with 0, then we can kind of incorporate that entire equation there into our matrix. Okay. In other words, we're going to replace that first row in the matrix with this equation. So we have 0. 0 is going to plug in for F1. And then on the matrix side here, we have 1, 0, 0. And then everything else is going to stay the same. So we have D1, D2, 3, 2, 3, A plus B, B, 0, B. And so since we have a constraint type boundary condition on node 1, then we replace that entire first row of that matrix with that boundary. And so if you'll notice, if you look at our new linear system on the right there, you can see that we've broken the symmetry. So it's no longer a symmetric system. And so this is something that'll be much easier to solve. All right, any questions on what we did here? Okay. All right, and so that's how you deal with constraint type boundary conditions. So whenever you have a fixed support or any kind of constraint or displacement, mathematically what's happening is that you're going to be replacing an entire row in a linear system. Okay. All right, so let's look at the other type of boundary condition, which is the low type boundary condition. And so remember the low type boundary conditions when we talked about it in ANSYS is any kind of force forcing term. Okay. And so whether that be just a literal force, it could be a pressure, it could be I know some people are playing around with torques on the midterm assignment, these all kind of fall in that category. Okay. But for our purposes, for at least for now, while we're doing springs and trusses, we're only going to consider force boundary conditions. And in fact, we're going to go a step further, and we're going to assume that those force boundary conditions are only going to be applied directly on the nodes. All right, so let me go ahead and draw our system one more time. One, two, three. A, B. So here's our two spring system. Okay, 3 nodes. We've already dealt with node 1, so node 1 is already taken care of. The other thing that we didn't account for yet, remember, is that we have a forcing on the system. So we're applying a horizontal force F, tensile force F, going to the right. Okay. And so if you look at this is basically saying that we have a force type boundary condition being applied at node 3. Okay. Let me kind of rewrite our current linear system. Actually, it's right here. So I'll just kind of scroll up a little bit. Okay. Okay. All right, so we have a force of capital F being applied at node 3. Okay. Luckily, by the way that we've kind of drawn our system, we already have a variable there that describes the force being applied at node 3. That's F3. Okay, so little f3 represents any force being applied on node. Okay. And so with that in mind, we can take our external force here, F, and then just replace little f3 by it. Okay. But once again, let me go ahead and draw our system here. So our first row where we find our constraint is 1, 0, 0. 0 on the forcing vector side. 1, D2. Okay. The other entries here are little f2 and little f3. Here we have minus KA, KA plus KB, B, 0. Okay. All right. And so if little f3, already represents the external force being applied on that node, let's go ahead and just replace that that variable. Okay. And so instead of little f3, we're going to have a we have just f right here. Okay. That's good. And so the only thing that we have to plug in for now is little f2. And so let's go back to our diagram here for our springs, and let's look to see if we have any forces being applied at node 2. Okay. And so if you look at node 2 right there, node 2 is the one right in between the two springs. We don't have any external forces being applied there, nor do we have any kind of constraints. Okay. And so what we can say is that F2 is equal to 0, right? There's no force being applied there. So let's go ahead and plug in 0 for F2 in our global units. Okay. So that's it. So now that we have the system in this form, we are now ready to solve. And so to kind of sum up what we just did, and so remember, for the constraint type boundary conditions, you're gonna take that constraint and replace an entire row in the linear system. For a load type boundary conditions, you only are going to input the forces directly into the forcing vector. Okay. And so when you have in load type boundary conditions, you don't make any changes to the stiffness matrix. Okay. So load type boundary conditions are actually a lot easier to deal with, just because you only have to insert them in one place. Okay. All right. And so technically, if we had numbers for this, we could solve the system. And so we have a system of 3 equations and 3 unknowns. But you'll be glad to hear that I actually don't actually force you to find the solution. So this is actually where I have everyone stop. Because even though you guys should know how to solve a system of 3 equations, 3 unknowns, it's mostly kind of a tedious exercise. So usually once you get to this point, I say that you're either done, or we may use either a calculator or MATLAB to solve the system. And we'll talk about how to use MATLAB to solve this in a bit. I used to factor MATLAB a lot more in this class, but this is the limit, because I know it's when some people hear MATLAB, kind of get stressed out a little bit, but we're just using it very, very minimally. And in fact, we're only using it just to save us some. But we'll talk about that in the next. Okay, any questions on this before we jump into another example? Okay, all right, so let's do another example. So let's kind of put it all together. So we've done kind of we've done kind of one example already, I guess, but then I was kind of narrating the whole time. So let's put it all together so we can see it all kind of happen. Okay, and so in this system we have a 3-element system. So we have 3 springs. Okay, so we're gonna have a fixed wall here on the left side. We're gonna have one spring come off the wall, and so we're gonna say this spring has a constant Ka. We're gonna say that this spring is gonna be connected to a wooden block. And this block is connected to 2 other springs on the right. So we have one spring like this, and another spring. Okay. And so the top one we'll call KB. The bottom one we'll call KB. Okay. So let's go ahead and label all of these nodes. Okay. All right, so starting from left to right, we have the node that's attached to the wall, so we'll call that node 1. The next node that we're going to label is actually the entire wooden block. And so we're going to assume that that wooden block is rigid. Okay. And so that wooden block is going to move together. We'll call this wooden block node 2. Okay. And that pertains to kind of everything here. So we're basically assuming that all 3 springs are connected together at that wooden block. So because they're all going to move together. Okay, we have the top node that's on the right side of spring B, so we'll call that node 3. And then we have the right node on spring C, so we'll call that node 4. Okay, and so in terms of forces on the system, we have 2 forces. And so we're gonna have one force that's being applied to the right on spring B, so we'll call that F3. And then we're going to have another force that's acting in compression on spring C. We'll call that F4. So since the last example we did with all symbols, let me give you some numbers for this problem here. So let me go ahead and label all these spring constants first. So we have Ka, the spring constant of Ka we'll assume is 500 newtons per meter. Kb we'll assume is 100 newtons per meter. Kc is 250 newtons per meter. Okay. And then for the forces, we have an F3. We're going to assume F3 has a magnitude of 100 newtons. And F4, we're going to assume has a magnitude of 15. Okay. All right. And so we're going to take this system here, and what we're interested in is we're interested in solving for the displacements or the deformations at every point. We want to find just how all of the nodes are going to move around as a result of this forcings and constraints. Okay. Okay. Any questions on just the setup for the problem? Okay. Oh.
This is what we can expect.
Something like this, yes. Yeah, so kind of the process that we're going to go through is basically what I expect us to do. And so we'll get it all the way up until this point. So we'll get it all the way up until the linear system. But I'm not going to ask you to actually solve that. So we'll just get up here. Okay. All right, so this is a very classical kind of direct stiffness problem. And so let's go ahead and apply our method. So the first step in the direct stiffness method is to discretize the system and label all of the elements and nodes. So that's already done for you. That's usually going to be the case. And so just to make sure that all of the answers are consistent, I do all the labeling for you. And so we can go ahead and jump to the next step, which is the element stiffness matrices. And so for every element in this system, we're going to write its 2 by 2 element stiffness matrix. Okay, so let's start with element A. So element A here is 2 by 2 element stiffness matrix. First of all, we know element A is connected to nodes 1 and 2. And so we're going to see that reflected in its element stiffness matrix. And so it's going to be F1, F2 vector is equal to. Element A is a spring. And so it's going to be KA, 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 KA. And since element A is connected to nodes 1 and 2, what we say is that this is multiplied by D1, D2. If you plug in for KA here, since we have its values, we have F1, F2, 2, 500, 500, 500, 100, D1, D2. Okay. Okay. So let's do the same thing for element B. And let's take notes on which nodes that KB is connected to. So element B is connected to nodes 2 and 3. F2, F3 is equal to KB, 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 2, 3. Okay. Of course, you can plug in for KB as well. So KB was 100, I think. So you can do that, but you know, just for the sake of time, I'm just going to leave it like that. And then we're going to do the same thing for element C. Okay. So element C is connected to nodes 2 and 4. So actually, this one's going to be interesting. Like these are 2 nodes that aren't, you know, directly next to each other in the number line. And so when we assemble this, it's going to be interesting. So I think we talked about it at the very end of class last time, but you actually get to see it in action when you have an element stiffness matrix like that, that's kind of separated out. Okay. And so for nodes 2 and 4, that means we're going to have F2, F4, AC, minus AC, minus AC, AC, E2. So that is the first step in our direct stiffness method, is to write out all of the element stiffness matrices. Okay. Usually the step is not that difficult. It's just a lot of writing, and so it's just kind of really tedious to write everything, especially if you're going to be kind of plugging in kind of ahead of time. Okay. So actually, kind of what I like to do is I like to kind of wait until the end to plug in, just to kind of limit the amount of writing that you have to do. But I know for some people, sometimes it helps to kind of see the numbers as you go through it. So you know, feel free to do that as well. All right. Any questions on this so far? Okay. All right. So let's move on to the next step. Next step is assembly. So let's go ahead and assemble all of these into one global linear system. Okay. Our global system here is going to be a little bit bigger than our last example because we have 4 nodes. Okay. And so since we have 4 nodes, that means our global linear system would be a 4x4 matrix, 4x4 linear system. All right, so let me go ahead and write that out. I'm gonna write it a little bit big just so to just to give us some room to kind of write stuff in. Let me label the columns too, just to okay. So here is our 4x4 system. Good. And so we're going to be basically inserting our element stiffness matrices into their appropriate spots. Okay. All right. So let's start with element A. We know element A is connected to this. And so we're basically going to look at the first 2 rows and the first 2 columns. Okay. And we're going to see where they intersect. And so they intersect at that box. And let's go ahead and write in the so I'm going to keep it variable form now, just so you kind of see. It's a little bit easier to kind of see what's going on. And then we'll plug, of course, we'll plug in numbers afterwards. Okay, so that's element A. Let's do element B. Element B here is nodes 2 and 3. And so element B, we're going to go to basically the second and third column and second and third row, and we're going to see where they intersect. And so they intersect basically like that. Okay. And so let's go ahead and write in the entries for element B here. All right, let me go ahead and leave a little bit more room because we know that whenever we have overlapping elements like this, you know, we're going to add their components. Okay. So in that one overlap square, we're going to have Ka plus Kb. And then all the others are no overlap. And so we have a minus Kb, and a positive Kb. All right, and then finally we have element C. And so element C we know is connected to nodes 2 and 4. Okay. So here's where it gets interesting, right? And so for all the elements so far, you know, we've drawn in kind of one kind of contiguous box for that element. Okay. When you have an element that's connected to, you know, nodes that aren't next to each other, you're going to have to break up that box. And so for nodes 2 and 4, that means we're going to be looking at all the locations of rows 2 and 4 and columns 2 and 4. Let me go ahead and box those. And so we're going to look at the place that's in the second row and the second column. So that's going to be this location right here. It's a big party on that spot, so everyone wants to be on that spot right there. Then we're going to go into the second row and the fourth column. So second row, fourth column is going to be right here. Then we're gonna go on the fourth row in the second column, so that's gonna be right here. And then finally, we're gonna go in the fourth row in the fourth column, which is the last one, right? Okay. So you can still, hopefully you guys can still see kind of the box. It's just we kind of expanded it to kind of fit this, to kind of hit the right spots in the global system. Okay. Because we're still going to write in the same entries. And so in the top left and bottom right, we're going to add a positive KC. So we're going to have plus KC on that big party spot. And then a positive KC on the bottom right, right there. And then in the other spots, we're going to have a minus KC, minus KC. Okay, so that's the top right and the bottom of the block. Right, and so that's all three elements. So everyone is accounted for. So remember, whenever you have an area that's not connected or not covered by an element stiffness matrix, we're just going to put 0. So we're going to have 0, 0, 0, 0, 0. All right, so that's the assembly step, and so we've gone ahead and assembled our linear system. Any questions on this step here? Okay. All right, so that's assembly, and so the last thing that we're going to do is basically the technique that we learned today, which is the boundary conditions. We have 3 boundary conditions on this system, and so we need to make sure that we account for them. Okay, and so the first boundary condition is a fixed support on node 1. Our second boundary condition is going to be a load type boundary condition. And so it's going to be a load of F3 being applied on node 3. And then finally, our last boundary condition, we have a second load. Okay. We have to be a little bit careful here because that load on node 4 is actually going to the left, right? And so even though we have our matrix system here, we're still going to respect kind of the positive and negative directions of the x and y. Well, eventually we get to the y direction, but for now we're going to respect the direction in the x direction. Okay. And so since F4 is being applied to the left, we're going to insert that into our linear system as a negative F4. And that's being applied on node 4. Okay. So that is that's all our boundary conditions. So let's let's go ahead and apply these to the to our system. Okay. Let's start with the constraint type boundary condition. And so the constraint type boundary condition is on node 1. And so remember, for constraint type boundary conditions, we're going to replace the entire row. So let's look at the first row of the matrix right here. And so our first row of the matrix right now is F1 is equal to KA minus KA 0, 0, multiplied by D1, D2, D3. All right, and so we have our fixed support is on node 1. And so that means we're going to put a 0 on every other column except for D1. And so in the D1 column, we're going to put a 1. And then on the left-hand side, instead of F1, we're going to set this equal to 0. Actually, let me write that down. So I think I didn't write that down. Over constraint calculations. Then replacing so when you're replacing the row for the constraint type boundary condition, put the 1 on whatever node is being constrained. And so if you do it correctly, what you should end up with is that the 1 should always be in the diagonal slot. Okay. And so if we kind of change this example, we're saying maybe we're going to apply a fixed support on node 4. Okay. In that case, we replace the 4th row of the matrix, and then we put the 1 on the 4th column, right? And so it should be the 1 should always be on the diagonal entry of the matrix. All right, and so that is that's the constraint boundary condition node 1. Let's go ahead and apply the boundary conditions on node 3 and 4. So these ones are pretty simple, and so we're just going to apply our X in the appropriate spot. So since we have a load of positive F3 being applied on node 3, we're just going to put a positive F3 in the forcing vector. Okay. And since we have a force of F4 on node 4, then we're just going to put a minus F4 on that slot. Okay. So the last thing, of course, is to replace middle F2. And so since we don't have any loads or any constraints on F2, we're just going to put a 0 in 4 for that. All right, and that's it. And so that's that is our answer. So of course, the last thing we can do is plug in the numbers. So it's actually let me go ahead and do that. So we plug in the numbers here. On the left-hand side, for the forces, we have a positive 100 in for F3, minus 50 in for F4. For the matrix, our first row is just 1, 0, 0, 0. 1, 2, 4. Second row, we have a minus Ka, so Ka is 500, so we have a minus 500. Next, we have Ka plus Kb plus Kc, and so if you add all of those up, so Ka we already know is 500, Kb is 100, and Kc is 250, so you add all those together, you get 850. 850 is on the party slot. And the rest of the row, we have a minus Kb, and then a minus K, minus 100, minus 250. Next row, we have a 0, 100, 100, 0. And the last row, we have a 0, minus 250, 0, 2. Yeah, so I always tell people, these problems, I think are, they aren't hard, at least from a conceptual point of view. It's very kind of automatic, or not automatic, it's very systematic because you're kind of following the same steps, every time. What is difficult is kind of almost the monotony of it is kind of difficult because it's a lot of just you're writing these giant matrices, you're plugging in, you're doing the addition, and so it's very easy to kind of make a very small mistake in terms of adding numbers incorrectly or putting a number in the wrong spot. And so these problems here, they don't necessarily test your intelligence. I say kind of it more tests your patience and your discipline. So but the problem is with these kinds of problems that if you make kind of a it can actually lead to a big difference in the answer. So I think and so a lot of times people panic when they do these problems because you go through all this work, you get these matrices, and you go into MATLAB and you solve it, and you get something that's very different from what I might have in the solution. So don't panic. That's usually because of kind of a small mistake. Okay. All right, and so if we solve this, so I'll show you how to plug this into MATLAB in a second. If you have if you know how to do this in your graphing calculator, that's fine too. And so if you solve this in MATLAB, you get the following results: D1 is equal to 0, 2 is equal to 1 meters, 3, 2, 1 meters, and D4 is equal to minus 0. All right, any questions on how we obtain any of that? All right, so let me so I think probably for the last thing we're going to do today, let me show you how to input this in MATLAB, because in terms of doing things by hand, this is kind of the extent that I kind of expect you to do. Okay. And so get to this point, get to the matrix system of equations, and then from there, you can either, well, technically you can leave it like that, but then if you want to check your answers with kind of what I'm going to post in the homeworks, you're going to need to plug it into that. So let me show you kind of the MATLAB way. All right, so let me go ahead and share my screen here. Stop. I've done this before. The MATLAB first. Stare at the MATLAB startup screen for a minute or two. Okay. And so to solve a linear system in MATLAB, you have to define basically two things. And so you have to define the matrix, of course, and then you have to define the forcing vector on the, well, for us it's on the left. So let's first define our matrix. Actually, let me see if I can do this. Define matrix. Good. Okay. So let me go ahead and give it a variable name. So we'll call it LHS matrix. And I'm going to define this matrix row by row. So that's typically how MATLAB likes to do. And so the first row in our matrix was 1, 0, 0, 0. Okay. And so I'm going to separate each entry by commas. And so I'm going to do 1, comma 0, comma 0, comma 0. Okay. So that's the first row in the matrix. And then to denote the next line, or to tell matrix that you're done with that row, you're going to put a semicolon after that. Okay, so 1, comma 0, comma 0, comma 0, semicolon. That means we go to the next. The next line is going to be minus 500, comma 850, comma minus 100, comma minus 250. Okay. Semicolon. And so that semicolon brings us down to the next row. So the next row is 0, comma minus 100, comma 100, 0, showing 1, 0 here. Okay, and our last row here is going to be 0, minus 250, 0, positive 2. And then once you're done inputting the matrix, you're gonna close it with a square bracket. You can put a semicolon at the end if you want. It doesn't matter. And so if you don't, then you can kind of display the matrix for you. And you can kind of check here to make sure that all the matrix entries are kind of what they should be. Okay. We have 1, 0, 0, 0 on the first row. Second row is minus 500, 850, minus 100, 250, minus 250. Okay. So everything looks good. Okay. So that is the matrix. And so let me go ahead and now define the forcing vector. And so our forcing vector here is going to be a column vector. So we're going to define it similarly to our left-hand matrix, except we're going to separate every entry with a semicolon. Okay. And so our forcing vector here is 0. Our first two entries are 0 because we have our boundary condition F2, and we have 100, and then we have minus 50. And then we're going to close it off with a square bracket. And once you hit enter, you should see the same thing. Okay. So now that we've gone ahead and defined our vectors here, we can go ahead and solve our linear system. So to solve a linear system in MATLAB, we will make use of the specialized backslash. Which is this one. And so if you don't know where the backslash button on your keyboard is, it's the button literally right above the enter key. If you're using the keyboards in the class, if you're using another computer, try to find the symbol that looks like. Okay, and so from there, it's very simple. And so now that we have our matrix, and now that we have our vector, and so to solve it, all we're going to do is we're going to put our matrix. The name of our matrix is, in this case, is LHS matrix. And then we're going to do backslash, the name of our vector. And then once you do that, MATLAB will perform a linear solve, and then it'll give you your solution here. And so the ordering of the variables here, the solution, should be the same as the order that you have on your hand calculation. So the first entry here is D1, the second entry is D2, third entry is D3. And the fourth entry is D4. And so if you check this with the answers that we got in the notes, they should be exactly the same thing. All right, and so that's just kind of the basics on how to solve linear systems in MATLAB. So just to kind of recap, first you have to define your matrix, okay, and you're going to have to use combinations of commas and semicolons to get there. Then you're going to define your forcing vector. And once you have those two things, you're just going to do one line of code where you just separate them with a backslash, and then that'll give you your answer. But of course, if you're more comfortable solving these in your graphing calculator, that's totally fine too. But if you don't have your graphing calculator, like me, so recently my graphing calculator that I've had since just recently died. So I'm very sad about that. That graphing calculator's gone all over the world with me. So it's a very sentimental moment, very sad. Okay. So if you're like me and don't have a graphing calculator anymore, you can use MATLAB to solve it this way. Okay. All right. Any questions on this? Okay, all right, so that's all we got time for today. So I don't want to start the next thing in the last 5 minutes. We'll save that for Tuesday. One announcement I want to make. So next Tuesday, I'm gonna plan on being sick next Tuesday, and so I won't be here on Tuesday because I'm gonna come down with the condition of gas is too expensive right now. So and they don't pay me enough to come here every day. So I'll be teaching from home. So Tuesday's lecture will be just purely virtual. So I'll send an announcement to let you guys know. Okay. All right, so thank you guys for coming today. I hope you guys enjoy your the rest of your day. Hope you guys enjoy your weekend, and I will see you guys next week. that's much. Okay. So what did you apply for graduation in day? And that's it. And so then, yeah, so then now your case. By your client to follow on. So Dr. Weiss has been kind of. So she's pretty on top of it, but on your end. Okay. Good.
Last night.
I'll be in E20.
Yeah.
Okay.
Oh, no, so I guess I'm just gonna say that and you did it through the student portal. Yeah. So I think there's a way you can do it offline, so maybe that's what. Yeah, but our department. You know. Exactly. Yeah.
What exactly, I mean, I understand that it's positive in the definition.
We're gonna assume it all stays kind of. Yeah. Exactly, yeah, so we treated this as kind of a purely 1D problem. We're gonna do 2D problems starting next. In those cases, you might have kind of deformation in X and Y direction, but for now, we're assuming it's completely rigid, it just moves like.
So in this case, I'm curious. Matter where.
Yeah.
I wanted to add that together.
So you could do that if you kind of combine these two springs together. So that would kind of give you the same net effect. At least on node 2. And so if you're interested in node 2, you kind of combine these two springs together. You basically just add their string constants. Or no, they're in parallel. So you would you would and then you get the net effect of that force.
Oh, I think so. It's just a little hard because I know like F3 is pulling the entire system to the right.
Yeah. And
F4 is pushing it to the left. But then F3 would also pulling this block to the right, which is then pushing on the same spring to the right, which would but F4 still the node still goes flat right. Right. If F3 was big enough, would it cause F4 to hold?
So F3 and F4, those are external forces. So those are independent of what the springs are. So, and so what's going to happen basically is that the top string is going to stretch because you're pulling on with F3, and then the bottom string is going to compress. So F3 and F4 are completely independent.
Okay.
But D3 and D4, those depend on kind of what the whole system is. So if you end up pulling F3 enough, then it's going to pull this block this way, and then that's actually going to push this F4 that way as well.
Okay.
Or
Even
the
though
D4.
you'll still the net difference.
Exactly.
Okay.
Yeah. So what we're computing here is the net movement. I think that up.
Okay. Thank you. So we're gonna need.
Okay.
So I just put some dummy formulas, so I don't have the actual meter. So here's already formula file. Quick calibrate the other one. There was something I should put it up or I have this similar. So my fix support is here. This is a very from the I mean, I don't know. So that's why the notebooks with the direct reinforces. Actually, so here and then here. I'm gonna come and see. Just wondering if so. You know, the material is 70.56 aluminum.
We find the definition on the bottom. So, I mean, magnitude wise, it's very small. So that's at least encouraging.
No, like, I mean, I figure not like, oh, I'm listening to this.
Let me see your.
I have more.
The regulations.
Nobody is.
And of course, like that. And then you listen to like the look out. So that's why the first is
But I guess it is a little bit strange that out from no force on the screen.
It's like, you should see the bottom.
Like Bryce, this is like. Is where Bryce is like.
So usually what I do, in these kind of situations is I try to,
I listen to a
kind
lot.
of isolate. So
Yeah, like a lot.
so you can kind of, it looks like you're kind of doing that already. So I like to kind of suppress the forces one at a time. And so let's do,
Even when she's like,
okay, so let's do a simulation to just see.
this is just like.
Because right now, it kind of seems like this force is not really doing anything. It's acting up here.
I know you.
It's not causing any deformation.
Yeah, I think I have tried, so you're today.
Yeah.
That's the information on, so then it's also possible.
It's just two, but it's still 7 steps. 7 steps. Don't you remember?
Which is possible, again, sort of, but
I mean, if you don't.
but the way it's kind of fixed and kind of set up here, so we expect kind of expect to kind of see something.
It's this, no.
We could probably do that.
It's this part that we have to.
With these ones, it's pretty easy to see, like, because I can see with the cat here, you have a lot of what's these areas right here. So the mesh, if you're not kind of careful, the mesh kind of concentrate on those areas. Because the way ANSYS sees it, it sees it as kind of a very small surface. And so it ends up with a very large mesh density. Whereas in other places here, one mesh density kind of we only have kind of one here. Okay, so it is deforming. It's just so small. And so the force here, so 1,000 down part of the same one. Force. Why should it be 2 separate parts?
Because this is the one that was like on is.
It's not 2 separate parts. Huh. But at least here it's one part. It's the third one. This is wondering if it has to do with the fact that there's just a lot more just material up there. So there's a lot more to and so even though you have about equal amounts of loads on both sides, everything here is basically shown. And so I'm wondering if that's what's causing more depth. I mean, what I was concerned about looking to see actually was that the top wasn't deformed. But it is. It's just really small relative to the other. So I'd say that's pretty easy.
This one, but.
And I think your mesh is fine too, because the main thing I would look at is checking mesh.
But the one with the two.
I check to see if you have smooth transition. And so you can see here that you have kind of the max deformation at the top, makes sense. And then there's kind of a smooth kind of transition to the bowl surface. That's good. A little stress here, like
So like you see on this.
sometimes if your mesh is too coarse, you're gonna see it looks kind of like choppy. That's kind of.
So we have the initially was
The
run,
one
so I had to do.
That's what I was referring to. Yeah. One have double.
Sizing the imaging certain parts that were like.
Because this
more basic geometry as opposed to emergency.
Gotcha.
So you get to the. And then I found out another thing. Staff.
Need fucking.
Scalar information. I was like. You ended up looking like.
Oh, yeah.
That also makes you honest by general.
Right.
And.
Did you just do the right?
I just.
Yeah, the auto scale message was it makes things look worse. I don't know why the auto scale is a default, because I think it causes more issues than it should be. I mean, the reason for that is because people like to kind of visually see their part. But yeah, if you're designing a part that's not supposed to deform, it can definitely cause some panic for sure. But yeah, it's good that you found the true scale thing. But yeah, no, I think this looks really reasonable right here. And I'd say the only difference is just attributed, there's just way more material up here. So, and so you're going to see a lot less deformation. Yeah, I think so. I mean, because this part, what's the material for this part? Steel.
70.
Okay. It's still pretty strong. So 1,000 pounds of force on something like that. I don't think it's going to cause, that much. Right. So I mean, right. And so I think before it was like maybe 2 decimal places. Yeah. So that's about kind of what. If you're feeling if you're kind of feeling uneasy about this, you can maybe increase all the loads by that. Maybe turn everything on. And if you see that deformations are not your deformation should increase by increase all of them. If it doesn't, then you might have some shear loss going on. Don't think that's the case. I mean, I'm guessing you have a quadratic mesh. You probably left it as default. Yeah. You can try this as quadratic. I think it does it automatically. Let's see if it makes sense. But it looks really, really nice.
Yeah, because a lot of what's there is from last year, the geometries. We can advance the same.
I
We
see.
don't have any on the hubs, so
Ah.
I guess with the housing.
I see.
So I tried looking for where I could reduce some volume, and I found that here was a little better. I feel a little uneasy doing it because we have some holes right here. You know, holes on the edge.
Right, right.
Because that's really top. I don't feel comfortable, moving the
Yeah.
the best place to do this from here.
Yeah, no, that definitely makes sense.
So all in all, even I said about 5 to 10, I feel like that might that should be enough, and if not, the variation we have is add a support member in between.
Okay.
To maybe the mirror the stresses is there, and there's specific work around just slightly up. It's a pretty easy one to do, especially in Australia. Stress and different factors.
French, yeah.
French, yeah, French. Basically the same.
Yeah, I wonder
If you wanna have.
this looks really nice.
Just take a French class. Yeah, I just kind of wanted to make a decision, because I'm like, if I'm doing this, and on my setup is it's very easy, that's what I said.
Yeah.
AP structural part, and basically English is not.
For sure.
So, yeah,
French man.
Yeah, it looks good. This is really nice.
I mean, with a few things
like,
just oh yeah, like
it's like,
something's feminine, something else is masculine. That's about it. Isn't it?
Yeah. Oh my gosh.
Perfect. I was just working through to try to, because it was very complex around some
I could understand.
basic
Let's
geometry.
say here, it's like.
Yeah.
I've seen like some shows. I knew that. I could understand.
Mesh.
Yeah.
Too much that is, not really.
Yeah.
Just issue, I had an issue. Just
Loading it.
But I can understand it.
And I can still run. It's just yeah, it's gonna take a while.
That's always with French. It's just like learning slang things.
Okay. If you want to, so the lab computers here, I know have a certain license grants, and so I think the only conditions actually go through was 100,000. So if you're, if you want to do kind of absolutely sure, you can try it on these computers, just like mesh it like crazy, and then I think you should get the same results. And then you know for sure that it's. But it looks beautiful.
That's kind of what I wanted to check, they were showing the losses in. Which makes sense, they don't look at a lot of stuff, my money.
Yeah.
As well, so now they can give it. I guess makes me more sad. A lot of those are getting signatures. So I had fixed.
Yeah.
It wasn't really fixing them.
Yeah.
So like, that's the guy, I have something wrong here. So that's what I saw about fixing the. Makes sense there.
No, that makes sense. That's definitely, that sounds like an issue. Fix it on this.
That's good.
Oh, damn. Nice. Getting these results in clutch. Yeah. That's fine. Yeah, you need the FDA.
Crutch on it a bit.
Yeah.
One there, I was like, yeah, you don't need that, at least for like everybody else. It's supposed to be theoretical calculations of this. But like,
That you need.
that, I kind of need something.
Yeah. Yeah.
I could,
Nice.
but
You wouldn't do it justice, it wouldn't. Oh, really? Oh, I'm done. Okay, I got it.
Fucking court.
Yeah, one time we don't show up.